In quantum mechanics, one of the most fascinating concepts is wave-particle duality, the idea that quantum objects like electrons and photons can behave as both waves and particles. Let's start with the famous double-slit experiment. Here we have a source that emits particles like electrons. These particles pass through two slits, and we detect where they land on a screen behind the slits. When we fire particles one at a time, we might expect them to create two bands on the screen corresponding to the two slits. And indeed, when we observe individual particles, they appear to go through one slit or the other, acting like classical particles. However, when we let many particles accumulate, something remarkable happens. Instead of just two bands, we see an interference pattern, alternating bright and dark bands characteristic of wave behavior. This is similar to what happens when water waves pass through two openings. This wave-like behavior is described by the de Broglie wavelength equation. Lambda equals Planck's constant h divided by momentum p. This means that every particle has an associated wavelength, which becomes shorter as the particle's momentum increases. In quantum mechanics, we describe particles using wave functions. The wave function, psi, gives us the probability of finding a particle at different locations. The square of the wave function's magnitude gives us the probability density. One of the most mysterious aspects of quantum mechanics is measurement. When we measure a particle's position, the wave function collapses, and we find the particle at a specific point. This is why we can't observe both wave and particle behavior simultaneously. Wave-particle duality reminds us that quantum objects don't behave like anything we experience in our everyday world. They are neither purely waves nor purely particles, but something fundamentally different that exhibits properties of both.